I'll be looking at the Legendre polynomials, the properties that they have, that they are orthogonal. There's our guy Legendre, who was born September 18, 1752 in Paris and died on January 9th, 1833. So he had a nice long life, and he did a lot in astrophysics and mathematics. Let's take a look at the inner product we're going to use. So we're going to show that these two two functions are orthogonal if their inner product is 0. And their inner product is going to be the integral from -1 to 1 of the product of the functions. Now let's take a look at the Legendre equation. It's 1 minus x squared y double prime minus 2xy prime plus k times k plus 1 y equals 0, where k is an integer and designates the particular value of the Legendre polynomial. And what we're going to do is notice something about this equation, which is that if we take and look at the derivative of 1 minus x squared y prime, we get these three terms. That is 1 minus x squared y prime. The derivative of that is 1 minus x squared y double prime minus 2x y prime. So we can rewrite the Legendre equation this way. And now we're going to assume that we have two solutions, a y1 solution and a y2 solution. And so we'll have two versions of this. And I'll put the 1 on this one. And then we'll write the y2 solution. So y2 goes with k2 and y1 goes with k1, and we're going to assume that k1 does not equal k2. That is, they are solutions of two different Legendre equations with two different k's, and what we want to prove is the integral of y1, y2 dx from -1 to 1 is 0, as long as k1 does not equal k2. And the way we're going to do that, we're going to take each equation and multiply it by the other solution. And so we're going to get two equations, and they're going to be 1 minus x squared y1 prime times y2 plus k1 plus 1 y1 times y2. Well, that equals 0. And 1 minus x squared y2 prime, the whole thing, derivative, y1 plus k2 times k2 plus 1, y1, y2 equals 0. Now, when we subtract these two equations, you're going to see we're going to get the y1 times y2 term, which we're going to integrate. So we're going to integrate both of these equations, and what we're going to notice is the following. If we integrate, we'll just take this first term. If we integrate that first term, that's a y2 here. Integrate that first term, it's of the form f prime times g. That is, it's of the form f prime of x times g of x dx, where f prime is 1 minus x squared y1 prime, and g is y2. And by using the integration by parts, we know that that's equal to f of x times g of x minus the integral of f of x times g prime of x dx. That is, we're using integration by parts. So we can rewrite this term and this term, taken that previous line, and we've integrated every term. There's actually two terms in each equation. Now we're going to apply the integration by parts to these first two integrals, and we're going to get 1 minus x squared y1 prime times y2 minus the integral of 1 minus x squared y1 prime y2 prime dx plus the integral minus 1 to 1 k1 plus 1 y1 y2 dx equals 0. So we've integrated by parts. Now we're going to have a similar one when we take the second. We're going to have 1 minus x squared y2 prime y1 minus the integral of 1 minus x squared y2 prime y1 prime plus the integral of k2 plus 1 y1 y2 dx equals 0. Now this first term is evaluated at minus 1 and 1 in both cases, and in both cases when I plug in x equals 1 I get 0 for 1 minus x squared, and when I subtract and plug in x equals minus 1 I get 0. So both of these terms are 0. They go away because at the limits everything is 0. So we were left with these two terms, and what we're going to do is notice that these two terms are the same. 1 minus x squared y1 prime y2 prime dx, and this one is 1 minus x squared y2 prime y1 prime dx. Well, those are obviously the same because I can reverse y2 y1 prime, y2 prime y1 prime, same as y1 prime y2 prime. So I'm going to subtract this equation from this equation, and these two terms go away, and all I'm left with is k1 plus 1 minus k2 plus 1 times y1 y2. Now if I factor k1 plus k1 plus 1 out of this fact and k2 plus 1 out of this term, I'm left with k1 times k1 plus 1 minus k2 times k2 plus 1 all times this common integral and that has to equal 0. Now we know that k1 does not equal k2, so k1 times k1 plus 1 minus k2 times k2 plus 1 is not 0. So the only way this thing can be 0 is if this integral was 0, which is in fact the inner product of y1, y2 and therefore we've shown that if y1 and y2 are solutions of the Legendre equation with two different k values, they are in fact orthogonal, or in other words, their inner product is 0.